Hi everybody. I'm Jared Hoberock from NVIDIA, where I work in the Programming Systems and Applications Research Group. And at NVIDIA, we have this sort of exotic, massively parallel architecture that we'd like to program. And one of the things that my group tries to do is to come up with programming models to program this kind of massive parallelism. And one effort that we've been sort of collaborating with is this effort to parallelize the C++ standard algorithms library, which is what I'm going to be talking about today. So how are we going to bring parallelism to C++? Well, this talk is about a technical specification for the parallel algorithms that we already know and love, that have been around for decades at this point, right? Algorithms like for each, sort, that kind of thing. This is actually a collaboration among multiple vendors of parallel systems and parallel architectures. And the technology that we'd like to standardize, at least, is based on sort of proven technologies from NVIDIA, Microsoft, and Intel. So NVIDIA has this parallel algorithms library called Thrust, which is a C++ algorithms library that's modeled on the STL and can target multi-cores and GPUs. Microsoft and Intel both have somewhat similar sort of parallel skeleton libraries that you can use to build a higher level, more abstract parallel algorithms on the parallel patterns library from Microsoft and threading building blocks from Intel. So we've basically taken all the ideas that you find in these existing technologies and found a way to apply them to the standard algorithms library. And the stuff I'm talking about today, there are multiple implementations in progress and that you can go find out on the web immediately. And we're targeting this technology for C++ 17. So hopefully in a few years, your compiler will be shipping standardized parallelizable algorithms library. So here's a short roadmap for my talk. I'm going to talk a little bit about what I mean by parallelism and what the parallel algorithms mean when they talk about parallelism. I want to show a quick motivating example, like why would you want to target these things in the first place? And how does it help you? How does it solve your problems? I'm going to do a short unboxing for you, show you what comes in the box, what you get with our current technology. I'm going to talk a little bit about the details and try to bring some precision to what we mean when we say parallelism and parallel algorithms, and then finish up with some future work. This is a work in progress, and we do know that there are some things that are unaddressed. I'm going to show you exactly what those things are. So what do I mean by parallelism? So that's like threads, right? Threads are parallelism. So I'm going to say no, threads aren't parallelism. They're two different things. So when I'm up here and I say parallelism, just think independent to yourself. Two parallel tasks are independent. They have essentially nothing to do with each other. You can execute both of them without interfering one with the other. And when I say concurrency, think of concurrency as an optimization that we can apply when we have some parallel tasks. And concurrency can be hard, right? So if we write a concurrent program, a program that has concurrent threads running, we have all these problems that we have to deal with, right? We have to deal with locking. We have to deal with exclusive access to resources. We have to deal with communication between the current concurrent threads. We have to solve problems of shared state. We have to make sure that our program doesn't have any data races in it. So these are all sort of hazards that get introduced when we start writing concurrent programs with threads. And hopefully these are the kind of hazards that we can avoid when we structure our code in a parallel or independent manner. So that's what I mean by parallelism. Just think independent. So the act of parallel programming, at least a working definition, is simply that process of identifying tasks which can be performed independently. And so the question is, how do I communicate this idea of independence to the system? How do I let the compiler and the library know that the things I want to do are actually independent? They can be They're parallel and they can be scheduled concurrently. It turns out it's easy. It's even easier. It's easier at least than parallel parking. It's that easy. So we want to make sure it's easy and that it's a simple and easy parallelism for everybody. Everybody can use this sort of thing. So the way we want to expose the parallel features in C++ is in a way that it's as easy to access as possible, and it makes simple things simple. It doesn't make simple things difficult. We want to make sure that these features are interoperable with existing codes, so there should be a very simple migration path to bring your sequential code, provided it's structured and expressed in a particular way. It should be very simple to migrate that code and parallelize it. At least that's the goal. Moving on, we want to make sure that this kind of parallelism can be supported as broadly as possible on sort of the broadest set of architectures out there. So we don't want to sort of unfairly bias one architecture that thinks about threading or concurrency in this way versus another kind of architecture that might think about it in a particularly different way. So we basically want to make the features as abstract and sort of general purpose as possible, just so that the greatest number of architectures and parallel systems can target it. And this means making concurrency sort of this invisible optimization that the programmer doesn't need to think about if they don't want to. Those concurrency tools like threads, locks, atomics, they're still there if you want to use them. You just don't have to use them to access any of the technology that I'm talking about today. And finally, since not every parallel architecture or parallel system works in the same way, we want to make sure that these features are vendor extensible so that if they wish, vendors of this technology can sort of provide vendor-specific implementation-defined hooks to get sort of more bang for your buck out of the implementation, just in a way that that's not necessarily standard. So let me show you a quick motivating example to sort of give you a crash course through all the features of this parallel algorithms library that I'm talking about today. So I'm at NVIDIA, and my background is in graphics. So I'm going to show a short example coming from the graphics world. So there's this algorithm from graphics called marching cubes. If you're not familiar with the algorithm, it's pretty simple. The idea is we have some object, say a bunny there on the left side of the screen, and we like to do something to the bunny. Maybe we want to draw a picture of the bunny. Maybe we want to bounce the bunny off the wall and the floor in some sort of simulation. But we can only do that if we have triangles, right? But we don't have triangles, we have a bunny. So how do we get the triangles? So what the marching cubes algorithm is going to do is to sort of overlay a grid of cubes over the bunny's surface. And we're going to march through each one of those cubes and apply a simple rule to figure out which triangles we should generate, just depending on how the surface intersects with the cubes. And that's a very simple parallel process. We just have a set of rules, a set of cases. We take a look at how the surface intersects with the cube and just spit out some triangles in a very simple deterministic way. And on the right side of the screen, what we get from that process is just what we call triangle soup. They're just a bunch of triangles. They're not connected into a graph or anything like that, just a bunch of vertices and the triangles connecting them. But the problem with marching cubes is, as I said, that it produces this triangle soup. These triangles aren't connected into a mesh. They're just a bunch of triangles. But usually what we want when we have some algorithm operating on a polygonal mesh is it wants a mesh. It just doesn't want triangles. It wants some connectivity information. So what we have at the beginning is this, this set of disconnected triangles there on the left side of the screen. And I need a way to weld them together such that the mesh is connected. So basically, I want to look through all the triangles, figure out which ones are sharing vertices, and then sort of collapse them together such that I have a single connected graph. And that's the actual solution. That's the actual thing I want to solve. So it turns out this process is pretty easy if you have the right high-level algorithms. Coming from a sequential programming background, we might have been thinking to ourselves, oh, I have to create some sort of exotic data structure, some sort of spatial data structure to keep track of all my vertices, figure out which ones are next to each other, and merge them that way. But in fact, we don't need any data structures for this algorithm at all other than a simple vector that we all know and love. And as long as we have the right high-level algorithms, we can do this very simply. So here's our procedure. First thing we're going to do is take all of our triangle vertices and sort them. Second, we're going to collapse, we're going to inspect our list and collapse spans of like vertices into a single vertex. So we're just going to throw out the duplicates, all right? And then finally, we're going to take what we had originally for our input and then just search the vertices for each vertex's unique index. And that's going to give us a single connected mesh, or graph, if you like. And you can do that right now with sequential algorithms if you structure your program this way. So let's take a look at how it works. The first thing I'm going to do is consider a vertex to just be two floating point numbers. So that's just a tuple of floats. So I create a vector of vertices. I just get that from the output of my marching cubes algorithm. And then what I want to do is have another vector of indices that's going to index into this vector of vertices. And we're just going to initialize that to the size of our input. So the first thing we do to solve this problem is to sort the vertices. And what this is going to do is that it's going to bring any duplicates together such that they form contiguous spans of vertices. And that's just a call to sort. Tuple's already sortable. Just throw it into sort. The next thing we do, moving down the slide, is to find the unique vertices and throw out all the redundancies. And since the vertices are sorted, we can do that with a single call to unique. So the unique algorithm is going to take, it's going to look at each one of those spans of equivalent vertices and just pick out the first one. So it's going to throw out all the redundancies. And once we do that, we can talk to our vector of vertices and tell it to erase all the redundant vertices, since the unique algorithm has basically sorted the thing into unique vertices up front and all the redundancies at the end. And then finally, to sum everything up, we want to take this list of unique vertices and then search it with a binary search to find all the indices of, find where in our output the original vertices were. And that's this call to myFind all lower bounds, and that's just a function I came up with. Okay, so now how do we do it in parallel? Well, you probably guess what happens next. We just tell the implementation to run all these algorithm calls in parallel, and that's pretty easy. We just bring these parallel algorithms into the bring their namespace into the set that we can work with the using, and then for the first parameter to each of these algorithm calls, we just use this par execution policy. So this is going to tell the algorithm that it's safe to parallelize the execution of this algorithm. And we just do that for each call to an algorithm. And we're basically done parallelizing our program. And if we changed our mind, we can jump right back. So in addition to the parallel execution policy, we also have a sequential execution policy. So we can force the implementation to sequentialize the execution of each algorithm call if we want to. But if we don't want to make that decision at compile time, we can do it at runtime. So instead, we can break out this execution policy type object, which is sort of like a dynamic container for more primitive execution policies. We can initialize this guy to seek. And then at runtime, we can make a decision. We can say, oh, well, the input is large enough. Maybe we want to allow parallel execution at that point. So we compare the size to some threshold and set it equal to par. And then just pass the container to each one of these algorithm calls. And the implementation under the covers will dynamically choose between parallel and sequential execution. But there's that one last call to find all lower bounds, which isn't a standard algorithm. Well, it turns out we can build that from more primitive algorithms that exist. So basically, the idea of this call is to run a lot of binary searches in parallel. So we're going to call the lower bound algorithm a bunch of different times for a bunch of different needles. We're going to search the same haystack. And it turns out that's just a call to transform, right? We call transform with each one of our needles. We pass a lambda. The lambda's job is to just take that needle and search the haystack. and then finally transform what it finds into an index. And then we're done. So it turns out this function is truly general. It's generic in data types via the iterators that we've used, but in addition, it's also generic in execution via the execution policy. So we didn't have to commit ourselves to any data type, and at the same time, we didn't have to commit ourselves to any particular execution. The same code works whether we want to run in sequential or parallel. So the sort of the point is composing our algorithms from lower level primitives basically gives us parallelization for free when we want to use it. So this is how I want to write parallel programs. Basically, I want to start with high level algorithms. I want to control how they execute via these execution policies. And then the last thing I want to do is sort of communicate dependencies, basically which algorithms depend on which other algorithms. And that's basically all I want to think about, right? I don't want to think about anything else that's going on underneath the covers, like threads, thread pools, locking, that sort of thing. So let me talk a little bit about what's included in the box when you get these features. You're going to get execution policies, which I've talked a bit about. You're going to get the parallel algorithms. And finally, you're going to communicate errors via parallel exceptions. So execution policies are pretty simple. There's just these additional parameters that you end up passing to algorithms when you want to talk about how they should execute. And right now, they're experimental, so they live in the experimental parallelism namespace. So up there at the top, you've got your vanilla sort of legacy sort. We pass sort 2 iterators. It sorts some data that happens sequentially today. If we want to explicitly insist that the execution be sequential, we can pass the seek execution policy. If we want to permit parallel execution, that's just the par for parallel execution policy. And then finally, if we're confident that vectorization is also safe in addition to parallelization, we can pass the parvec execution policy there at the end. And those are the basic execution policies that we're providing. And then we also have this dynamic execution policy, named simply execution policy. You can change its value at runtime, maybe depending on some threshold if you like, and then pass that to sort and control its execution dynamically that way. And then finally, we also allow for implementation defined or non-standard execution policies. And here's just some example of some that you can imagine vendors providing. You might imagine a vendor providing a policy that would vectorize an algorithm but not allow any new threads to be created. So basically vectorize in this thread only. If you had a thread pool that you already had pre-existing that you wanted to make sure execution got scheduled on, that's the kind of thing that you could pass through an implementation defined policy. Obviously, GPUs, if you want to take advantage of parallelism on a GPU, that would be something that would be non-standard. Or even an FPGA. Basically, none of the algorithms would preclude that sort of thing. You might imagine uploading a computation to the cloud. Or if you're feeling ornery and your vendor supports it, you could launder this sort through a botnet, if it's supported by your platform. So what is an execution policy exactly? Well, it's a promise that a particular kind of reordering will preserve the meaning of a program. And I'll talk more precisely what I mean about that in the coming slides. And at the same time, an execution policy is sort of a request that the implementation use some sort of strategy while it's executing the algorithm. So what sorts of reordering are allowable? What exactly am I talking about? Well, let me show you the details. Let's start with sequential execution. So suppose I have some invocation of some algorithm, and I've passed seek, meaning that I want the execution to be sequential. I pass some iterators and maybe some function that I want it to call. Well, when I say seek, that means that the algorithm has to invoke the functions and whatever iterator operations it needs to do in sequential order in the thread that actually called the algorithm. So but graphically there on the right side of the screen, you can sort of visualize what I mean by that. So the calling thread comes in, calls algo with the seek execution policy. We sort of switch to the algorithm, and within the same thread, the algorithm must invoke that function sequentially. So that means that Once the algorithm has started invoking the function once, it has to finish that invocation before it's allowed to start a new invocation. So each invocation basically happens before the next one. And then finally, and sort of time flows down the slide in this diagram. Then finally, when the algorithm is done, it synchronizes with the caller. So there's no asynchrony going on here at all, and it's sort of finished. So that's basically the simple sequential execution. We can move on to parallelizable execution and talk about what's sort of allowed here. So when we make a call like this, algo of par, that means that the algorithm is permitted to invoke the function unsequenced if it happens to do so in different threads, and in indeterminate order if it happens to do so in the same thread. So what exactly does that mean? It makes it a bit simpler if I show a similar picture from before. So if we come in with our calling thread and call algorithm, it's basically saying that the implementation is allowed to create whatever threads it wants to execute this algorithm. And each of these threads is sort of tasked with invoking the function or maybe manipulating the iterators. But the thing is that there's no sort of global time anymore. So time proceeds sort of locally within each of these threads. So within each thread, each function invocation is ordered, but we can't talk about any sort of ordering between threads because each thread has sort of its local notion of time. But still, within a thread, we can rely on a sequential order, but we can't know what order it actually is. So it's basically the caller's responsibility to make sure that that's safe, right? So we can't call an algorithm that will introduce data races or deadlocks because of those rules. So for example, this is the kind of code that would introduce a data race. If I invoked a parallel for each and tried to do pushback into a vector in each invocation of this lambda, that's going to be a data race because the pushback function assumes that the caller has exclusive access to the vector. But that's not true anymore in a parallel for each because we might have multiple threads interacting with the vector. So one way that we could fix that is to use a mutex and basically insist that we have or we have exclusive access to the vector. But of course, that will turn our parallel for each into a sequential for each. So I don't advise doing that. Instead, do something like this. Basically resize the vector beforehand, and then we can write to it within the lambda in parallel without causing any sort of data race. Another example of something that might deadlock is this piece of code. So assume that we were kind of feeling mischievous and called a parallel for each and wanted to insist that the lambdas that were the for each invoked were going to be invoked concurrently. So one thing we might try to do is sort of increment a counter each time that the lambda gets invoked, and then sort of wait for everyone to arrive. But it turns out that that's not possible because all of these lambdas could have been invoked on the same thread, right? So we'll end up spinning forever and deadlock. So don't do that sort of thing. Do something else. Do you have a question?
What kind of conditions do you guys use to know how many threads to create for, say, a parallel algorithm?
So the question is, how does the parallel algorithm know essentially how much concurrency it needs to create, how many threads to create? That's entirely up to the implementation. And I imagine vendors will each have some black magic to choose that kind of thing. One good rule of thumb is to not create more concurrency than you have cores beyond some threshold. So say if I had 8 cores, I might only want to create 16 threads, that sort of thing. More question?
So earlier on, you had the ability to dynamically select an execution policy, but one of those execution policies involved vectorization. How is that implemented?
So the question is, we had a vectorizable execution policy. The question is, how is that implemented? It can't be implemented using any standard means, right? There's no support for vectorization within the standard, so it's going to have to be implemented with vendor-specific black magic, right? So on a GPU, maybe it's implemented with CUDA or C++ AMP. Intel might, use SIMD pragmas or SIMD for loops to implement it, that sort of
So
thing.
I was more worried about the fact that if you're dynamically selecting something that requires alternate code.
Right. So the question is, you might not need to compile the function in a particular way to vectorize it. That's incredibly. You're absolutely right about that, and there's nothing. We're sort of agnostic in our specification about how that happens. Basically, it'll be up to the vendor to figure out what needs to happen to make sure that that's possible.
Can the execution policy have information like, about a specific thread pool or a specific GPU?
Right. So the question is, what information does the execution policy carry around in it, and what exactly information would that be? Basically, in version 1 of this technology, we're entirely agnostic about that, but we envision integrating scheduling concerns in with it later. Okay, so finally I want to talk about parallelizable plus vectorizable execution. So this is sort of a refinement of parallelizable execution. So when I make an invocation like this, it means that the algorithm is permitted to invoke the function unsequenced in different threads. But if it happens to invoke the function within the same threads, it's also unsequenced. So there's no ordering at all. And so that's what that diagram looks like. So we have multiple threads, but even within a thread, all the function invocations are essentially happening on top of each other. We can't find an order, so you can't really rely on an order. And that's basically the difference. And again, it's the caller's responsibility to ensure that this sort of thing is correct, and I'll show you some places where that might not be. So for example, if we tried to use a mutex to get exclusive access to this counter, this is going to fail and deadlock if this lambda happens to be vectorized within the same thread, right? Because the first SIMD lane will come in here, take this lock, and at the same time, maybe the second lane tries to do it at the same time, but that thread and that'll cause that thread to block. So don't do that sort of thing. You can use an atomic, that's safe, but again, you should just use a higher level algorithm. If you're trying to count something, just use the counting algorithm. So what parallel algorithms are we talking about? Basically, we're providing overloads of every algorithm in the existing library to the degree possible. So basically, we want to parallelize everything. But we do have some new algorithms. There's 3. The first one is reduce, which performs a reduction over a collection. If you're not familiar with the idea of a reduction, we're basically taking a collection of items and reducing them into a scalar. So it's basically something like a sum. The next 2 are 2 prefix sum algorithms, exclusive scan and inclusive scan. And basically, these are a little like the partial sum algorithm, but differ in how the semantics differ in how they treat each individual element of the sum. There were some algorithms we're not able to parallelize: binary search algorithms, heap algorithms, permutations. Shuffling, and some of the numeric algorithms. We just didn't find any parallelism there, so they don't have an overload. Running out of time, so I'm going to blow through these parallel exceptions part. Basically, when an exception occurs in a parallel algorithm, it's a bit differently from a sequential algorithm because there could be multiple exceptions in flight if there are multiple threads in flight. So we need to collect these exceptions together into a list or a collection and throw it back to the calling code. So here's an example of a sequential for each that throws an exception. We can just catch the exception. But if we tried to parallelize that, instead we need to catch this exception list, which is essentially just a list of exceptions. And maybe we can process them and handle them in a reduction there at the bottom. And of course, that also works with the sequential execution policy. It's handled in a uniform way. To sum everything up, I want to show a quick example for estimating pi using some high-level algorithms. So if you remember from elementary school, the area of a circle is pi times radius squared. And we can use this equation to estimate the value of pi. So one thing we might do is to take just a section of the circle, just a quarter of the circle in the unit square, and then just start throwing darts at the unit square. and then just count up the number of darts which happen to fall in the quarter circle. This is going to allow us to estimate pi. It's just 4 times the number of darts that fall within the quarter circle. It's nice because you can do this with a single reduction. So basically, we want to write a function that will test whether a point is within the unit, lies within the quarter circle. So this is the test quarter circle function there on the left. It takes some sort of seed. We're going to generate a random number. And incidentally, this is a really terrible way to generate parallel random numbers. But it's a great way to do it if you need to do it in a talk on a slide. So what we're going to do is seed a random number generator, and after hashing the seed, just with a hash that I picked up off of the internet, and then draw 2 real numbers within the unit square, and then just measure the distance from the origin to that point. And if it's within 1.0, then this point lies within the quarter circle. So all we have to do to estimate pi is just count the number of points that pass this test. So we can throw, say, 300 million of these darts, make a counting iterator to generate the integers 0 up to n, and then just call COUNTIF with our test. And this is just going to count for us the number of points that lie in the quarter circle, and we can estimate pi just with some arithmetic. And then we can take a look at the performance. So there on the left side of the screen, I have a single CPU thread running on an i7. We can test 300 million of these points in about 5 seconds. If we want to parallelize it with the PAR execution policy, we get about 5 times speed up, which is a pretty nice speed up, I think, for basically no work at all. We just had to change that execution policy. And then finally on the right there, we can use lots and lots of GPU threads and run it on a GPU, and we get almost a 20 times speed up from the single CPU thread. So this is a good argument that writing your algorithms in this style will let you get some degree of performance portability for free without having to target the details of the underlying parallel architecture. And so there's quite a bit of future work. One thing I hinted at before is this problem of how to schedule these parallel algorithms. When we call a parallel algorithm, this algorithm sort of needs to compose with the scheduling decisions in the surrounding application somehow, right? But all we have is this execution policy argument. So how do we do that? So the execution policy specifies how the algorithm is allowed to execute, right? It gives conditions on how the algorithm is allowed to call that function and in what order it's allowed to call it in, but it doesn't say where it can call that function. It doesn't say what threads it can get scheduled on. So this idea of choosing where to place algorithm execution is orthogonal to these other concerns that we have. So one thing we've been thinking of is a way to compose scheduling with our execution policies simply by parameterizing them in some way. For example, we could pass them as an argument to the execution policy. We anticipate doing this in the next version of this specification. So in this case, in an invocation like this, the sched parameter would specify where the work should be executed. So this is where you might stick your thread pool if you had something pre-existing. So the scheduling parameter could be a hard requirement to execute vectorizable work in the current thread. If you didn't want to spawn extra threads, you want to vectorize in the SIMD unit within the current thread, you could mandate that with a scheduler. It could tell the implementation, this is the number of threads that you're allowed to use in this invocation. Don't generate anything more. You might want to do that to avoid overloading your system with threads. Again, it could be a thread pool to use. There's sort of a separate effort within the ISO standardization committee to standardize this concept of an executor, this thing that will execute function calls for you. It could be something like that, or it could be a requirement to use this or that GPU, or maybe a set of GPUs. So as I mentioned, there are a few implementations of this technology in progress. One is on GitHub. At that address, it's based on the Thrust library underneath. One is on Codeplex from Microsoft. Turns out it's not based on the PPL. It's based on Windows, a more primitive threading pool implementation. And then I know of another implementation on GitHub based on C++11 threads underneath. You have a question?
Yeah, just to point out, there's one more implementation actually with HPX. I've been working on it for about half a year.
Okay.
There's one built inside of HPX, so that's the same.
Please repeat.
So he's just pointing out that the HPX project has their own implementation. I assume that's somewhere on GitHub?
Yes.
And it's also on GitHub. So GitHub has all the code, except for the Microsoft implementation. To sum up, if you code your parallel programs using high-level algorithms, you're going to make it really easy on yourself to make that code scale as architectures change and get wider and wider in the future. My feeling is that these algorithms make your code portable and composable sort of at the same time, and it also makes all these questions of concurrency invisible to you if you want them to. As far as standardization, we think that this specification is on track for C++17. In the meantime, we've prepared a technical spec in the meantime, and it's experimental. And if you are interested in the gory details, you can find it and read it there on GitHub. Okay, so that'll wrap it up, and I'm open for questions.
Okay, so my question is, on one of the slides you had this a piece of code that said if the number of elements is bigger than some threshold, use the parallel execution policy. Now, this decision is not usually just easy to make. It's based on the underlying architecture, on other considerations.
Right.
So, do you really you have this wonderful generic abstract way of specifying execution, and then you have to make the programmer decide based on some arbitrary magic that I want to use this or that one, without the programmer actually knowing, anything about the hardware, because we're too high up, too abstract.
So the question is, we have this dynamic execution policy. I showed an example where the programmer has to make a decision about how to parallelize. How is he supposed to make that decision? It's a hard decision to make. I completely agree with that. It's basically a tuning decision, right? You have to, if you're treating basically the implementation as a black box, it's sort of an auto-tuning problem. You basically have to just search this space, figure out where it makes sense to parallelize. And that sort of thing is hard. But at the same time, it's the kind of thing that a not insignificant portion of the audience is going to want to do. So that's why we make it possible to do that sort of thing. If it were me, I would just use the parallel execution policy all the time and don't even worry about that sort of thing.
It seems like there's a logical join, essentially, synchronizing at the end of each algorithm, but you may have multiple independent algorithms that you wanted to share the resource to make better use of those resources, and then manually join at certain locations.
Right.
Is there any way to do that?
So the question, or the observation was that these algorithm invocations were all synchronous, right? They have to synchronize with the caller. You can't get asynchrony in this interface unless you wrap it in something like async, right? But that introduces overhead. This is, especially coming from my background, this is especially important on GPUs, right? You don't want the CPU to wait for the GPU to do something before it can tell the GPU what the next thing to do. So I think there's room for a sort of a separate asynchronous interface to the algorithms, but I'm not sure if anyone else thinks that.
Hi, a little bit on that note also. Is there support on, or are you thinking of adding support for memory management? Because I'm thinking about those consequent invocations of the parallel algorithms, especially for GPU. Can we say something like, keep that memory in the GPU? Because I'm going to use it next.
Right. So, question is, how do you control temporary memory allocation that the algorithm might need to do to accomplish what it needs to do? So in my implementation, that's just that's just been an allocator that you can pass to the execution policy. It sort of takes ownership of the allocator, and it uses that allocator anytime it needs to allocate something. That's something that could be done through an extension. And then maybe in a future version of this technology, it could be incorporated into it somehow. Okay, thanks everybody.